Hi and greetings, Prof. Debarajan. My name is Muhammad Tariq Nazmi bin Abdul Rahman, MH19055. Me and my team members, Group 5, will present our project proposal about Proton Saga 1.3. What is EV and EEV? An EV is a shortened acronym for an electric vehicle. EV is a mode of transport which is powered by electricity, unlike conventional vehicles that use gasoline, that is petrol, or diesel-powered engine. Electric cars use an electric motor powered by electricity from batteries or a fuel cell. A key advantage of EV over other forms of transport is that they hold the potential to significantly reduce pollution by having zero exhaust emission. EEV is an energy-efficient vehicle. The Malaysian Automotive Institute (MAI) defines EEV as vehicles that meet a defined specification in terms of carbon emission level and fuel consumption. EEV includes fuel-efficient vehicles, hybrids, EVs, and alternatively fuel vehicles such as hydrogen and fuel cell. There is four types of EV. The first one, battery electric vehicle (BEV). Second one, hybrid electric vehicle (HEV). The third one, plug-in hybrid electric vehicle (PHEV). And the last one, fuel cell electric vehicle (FCEV). Battery electric vehicle (BEV) is fully powered by electricity. These are more efficient compared to hybrid and plug-in hybrid. Example of cars is Nissan Leaf and Tesla Model S. While hybrid electric vehicle (HEV), this vehicle use both the internal combustion engine and the battery-powered motor powertrain. The petrol engine is used both to drive and charge when the battery is empty. These vehicles are not as efficient as fully electric or plug-in hybrid vehicles. Example of this car is a Toyota Prius and Honda Jazz. Plug-in hybrid electric vehicle (PHEV). This one use both an internal combustion engine and a battery charge from an external socket. They have a plug. This means the vehicle battery can be charged with the electricity rather than the engine. PHEV are more efficient than HEV, but less efficient than BEV. Example of the car is a BMW 330e. The last one is fuel cell electric vehicle FCEV. FCEVs are powered by hydrogen. They are more efficient than conventional internal combustion engine vehicles and produce no tailpipe emission. They only emit water vapor and warm air. Example of car is Toyota Mirai.
Good morning, my name is Shobhan Gopal Krishnan. My metric number is MH19054. Today I'm going to present about national automotive policy. Okay, they got 5 steps. Supply chain integration, where the export of vehicles, components, and spare parts and more on. Second is the local manufacturing, that increase the local production of the automobile in our local manufacture. The third one is engineering capabilities, that improves the local engineer R&D, testing, and technology development capabilities. And the latest technology trend that utilized IR 4.0 technology to adapt and emulate the newest technology trend. And the last one is sustainable development, where utilizing the environmental friendly product and process to minimize carbon emission. Okay, there are 5 objectives. The first one is to develop an NXGV technology system to make Malaysia the primary production hub in the region, increase the MAAS sector involvement, make sure the local automotive industry is prepared with a new paradigm that's called development of IR 4.0, ensure the development of NXGV has a positive impact on the entire ecosystem, and by 2025, Malaysia will lower vehicle carbon emission by increasing the fuel economy. There's a new element in the NAP to, like I said before. First is the next generation vehicle NXGV, where the energy efficient powertrains, advanced driving capabilities, and a connected vehicle, and the mobility as a service (MCAAC), mobility as a service transportation that is consumed as a service, preparing for new ownership model. The third last one is Industrial Revolution 4.0, where the smarter and the leaner manufacturing business that are future proof and competitive in global. Next, we see the drag coefficient. Drag coefficient is to calculate the distance of as an object moves through a fluid. Is to calculate the aerodynamic drag as well as the effect of form till the flow condition. We can see the formula here, CD formula. The drag coefficient CD is calculated by dividing the drag D by the following formula: density R time F, the velocity V squared time the reference area A. The drag coefficient thus expresses the drag force as a ratio of the force produced by the dynamic pressure time area. Next, we see the lift coefficient. The lift coefficient is dimensionless variable in a fluid dynamic that connects the lift created by lifting body to the fluid density surrounding the body and the fluid velocity and also the associated reference area. It's determined by the body's angle to the flow Reynolds numbers and the Mach numbers. We can see the formula here. The lift coefficient is calculated by dividing the lift L by the following formula: density R time half the velocity of V squared times the wing area A. The lift coefficient thus expresses the lift force as a ratio to the force produced by dynamic pressure time area. The last one is a Hammett body. Hammett body is a simple vehicle model based on the basic car body. The analysis, the work identify and characterize the airflow around the Hammett body, which capture the main flow properties around the automobile. Allow us to capture characteristics that are relevant to body in the automobile industry. It can be easily used for exploring many properties such as turbulence, drag coefficient, lift coefficient, weight region, lift force, velocity magnitude, and various parts of the automobile. And also we can magnitude of the pressure around the car. So in this case, we will see the drag coefficient and lift coefficient. We can see the graph over here is we can see the lift coefficient is the value is 0.3286 something, and the drag coefficient we can see the 0.284808. So we can see the difference between the lift coefficient and drag coefficient in the graph. Thank you so much.
Hi, my name is Fazrul Hassani bin Kamal Zaman, metric number MH19058. I'm going to continue with my part of the presentation, which is car we have chosen to better the energy efficient vehicle, which is Proton Saga 1.3. This current model is the third generation of Protons, which start manufactured at 28 September 2016. So, for the engine specifications, the Proton has 4 cylinders inline with 16 valve double overhead camshaft with variable valve timing. It has a displacement 1.3 liter and 4-speed automatic transmission. Next, this is the chassis, dimension and weight specification for our vehicle chosen. Our vehicle complete with safety and security features as listed in the slide, except for reverse camera and front parking sensor. The EcoDrive Assist system is one of the interior systems for technical specification that makes it energy efficient, which is controlled by ECU. ECU mode also will reduce the aircon efficiency to 70 to 80%, which will result to less energy power usage and saving fuel. Next, I will continue to talk about dimension blueprint. Automotive design begin the design process with hand sketch before using computer-aided design program. The slide shows the blueprint for a Proton Saga 1.3. Now, we will continue to ways to produce energy-efficient vehicles. Firstly, is aerodynamic optimization of Proton Saga 1.3, which is aerodynamic drag reduction by round the edge of the front end, add side skirts, lowering the vehicle, and etc. Next is rolling resistance optimization by using low rolling resistant tire that maximize durability and riding comfort to increase fuel efficiency. Lastly, installing the stop-start system. The stop-start system might be the most effective remedy for energy-efficient vehicle. This stop-start system has the ability to turn off the engine when it has halted, like at a stop sign such as traffic light. The technology provides a quick engine restart for the vehicle's take-off. That's all for me. Thank you.
My name is Falik bin Muhammad Hisham, and I will continue with the flow simulation procedures. So first, with the model ready in the SolidWorks Inventor, first thing you need to do is to activate the SolidWorks Flow Simulation by going to the SolidWorks add-ins and activating the SolidWorks Flow Simulation. Then you will have this step. So from this step, the second step is to create the new wizard. This is where you can put the project and the command. Then we need to select the SI unit. Next, we will choose for this type of experiment, we will do external analysis, and we take this exclude cavities without flow condition and exclude internal space. Next, we will choose the type of liquid, which is gases and air. So we double click that and we click next. So for this, we click next also. Then we will put the parameter which is in z-axis 30 meter per second, and we will click finish. Then the next step is to set the computational domain, which is this is the computational domain. So to set that, we go from the right side, we zoom out a bit, computational domain, edit definition, and we will need to just pull the arrow about leaving space about the body, half of the body, right? Then we will adjust it from the front view. Okay, then after we select the computational domain, we need to set up the global goals, which is from here. Insert global goals, and we will find normal force x and y. Normal force, I believe, or no, it's y and z force. Y is the brake force and z is the drag force. Then we will click tick, and then we will need to run the solver. So to run the solver, we need to right click on here and click run and run. So they will take some process, and I will meet you once it's done. Hi, my name is Fali, and now I am back. Now that we have run the analysis, now we will see the cut plots and the flow trajectories. To do that, we will right click on cut plot, select insert, and from this we will click these three here and selecting the right plane, and the contours will be, we will choose a pressure and right. So this is our cut plot, and here you can right click to show minimum and our maximum. So our maximum is 101858.919 pressure, and our minimum is 100980.6728. Okay, so now we will see the flow trajectories here. For the flow trajectories, we use the front plane with 500 density and spheres. Okay, so we will animate this. So this is the flow trajectories of our model. Okay, continuing with Ahmad body, our cut plot will have a maximum pressure of 102,056.59 PA at the front end, and minimum pressure of 100,864.81 at the rear end. Continue with our flow trajectories. Our flow trajectories will be like this. So for further explanation about the result, I will give to Shavin, and that's all from me. Thank you.
Hello, my name is Shavin Ramaya, entry number MH19052. So I'll continue with my part of the presentation, which is the flow simulation analysis methodology. So there are three types of analysis we will do for our models. The first one is the contour plots, which is simply using these color codes, which will be shown in the flow simulation analysis. So the blue color from the lowest pressure to the red color, the highest pressure, applied on the location of the parts of the model. So the second one is the coefficient of lift, CL. This is we get these values by using this formula: 2 times L lift force over density times speed square times frontal surface area. Then the third one is the coefficient of drag. This the same formula. We will just change the lift force to the drag force. So from already what we have done to the original Proton Saga model, we get this summary table of lift force data, average, minimum, and maximum lift force in Newton, and also the drag force. So using these formulas as shown, so this is the table of the lift force that we will get in the Excel version. So using the formula and this lift force, we will get these values of coefficient of lift and coefficient of drag for 4 different speeds. There is a 10 meter per second, 25, 40, and 55 meter per second. So this data is only for the original Proton Saga model. The procedure is the same for the Ahmad body as well. So let us see some parameters that are fixed and manipulated. So for the fixed is the flow fluid is air. So the air density is fixed, 1.204 kilogram per meter cube. To calculate the frontal surface area, the formula is 0.9 times height times drag of the model. So for the original Proton Saga, the frontal surface area is 1.97 meter per square. So for the Ahmad body is 0.1008 meters square. Meanwhile, for the improvised Proton Saga, we still haven't found out yet. It will be only known after we have modeled the improvised EEV Proton Saga version. So from the table just now, we can plot these graphs. This two is for the original Proton Saga model. The lift coefficient was 4 speeds and drag coefficient was 4 speeds. And these two graphs is for the Ahmad body. So from these graphs, we can extract the average CL and CD values for original Proton Saga as well as the Ahmad body for 4 different speeds. So for the final project, we will add one more third data, which is the improvised Proton Saga version. So from overviewing this data, we can see that the original Proton Saga model has less lift coefficient compared to the Ahmad body, which may be due to some error of modeling the Ahmad body. But however, we can see the drag coefficient for Ahmad body is better than the original Proton Saga because Ahmad body is the ideal vehicle shape. So our improvised Proton Saga should have the values in the range of Ahmad body or just lesser than the original Proton Saga values. And that is all for our project proposal. So the expected results and discussion to further accomplish our projects are: number 1, modeling of the suggested improvement to the original Proton Saga's exterior body to make it an energy efficient vehicle. 2, comparison of contour plots, lift coefficient and drag coefficient values between all 3, original Proton Saga, Ahmad body and the improvised Proton Saga model. And lastly, discussion on the success rate of improvement modeling and feasibility in the real life automotive engineering industry. So that is all. Thank you very much.